So we're talking about dilations here today, and we have vertical stretches and compressions. We are beginning with multiplying the outputs, which are the y values, by a. That's if the a is in front of the parent function and it is a number greater than 1. Down here on the bottom left corner, that would be example 3a. So what we're going to do is we're going to graph this now. Go to Desmos and put in y equals x squared and compare it to y equals 3x squared. And we'll see what it looks like in this step. So we're looking here at the difference between x squared and 3x squared. Y equals x squared is in red. Y equals 3x squared is in blue. And one thing that I want to do is trace in, I'm going to trace in red. Just follow me here. Some key points on the graph. 0, 0, 1, 1, 2, 4. Way up, almost up the screen, right up there, 3, 9. The outputs, y, are the inputs, x squared. You'll notice that on the blue function, however, the key points are 0, 0, 1, 3, 2, 12, which means it's off the screen up there, and 3, 27 is way up there out of view. We would have to scroll up to see it like this. Let me prove that they're there. Right here. Right here. Right here, you'll see the point. Right here. 212. There it is. 2, 12. Hold steady. 2, 12. All right. If you go way up above 25 there, you'll see the point 3, 27. All right, on the blue function. That is because the x's were input. You square that input and then multiply by 3. In a table of values, it would look like this. Ready? When you put in 0, 1, 2, and 3 for x. In red, you get 0, 1, 4, and 9. But in blue, all of those y values are going to be tripled. And that is what's known as a vertical stretch. 3, 12, 27. Let's continue our discussion and talk about a vertical compression. And that's the next one I'm going to reveal here. How does that work? Well, we still have the a out in front of the f of x, multiplied by f of x. However, this time a is a value between 0 and 1, like 1/2, 0.75, 1/10, 0.99. Any number like that is going to take that parabola and shrink it down, all right? Compress it. As it does that, it will naturally widen it as well. Imagine you're sitting on the parabola. It's like a chair, and you sit down on it. Well, you go into the cushion, and it squishes it down and widens it out that way. So let's see that in action when we go here and graph 0.5x squared. Here it is for those of you watching on video. We jumped right to the graph here. 0.5x squared. You can see that now the blue parabola is wider and flatter. It has been compressed vertically. Watch what happens if we just remove the decimal point for a moment. Gone. Steep. Back in. Compressed. Stretch upward. Compressed downward. So that fraction value in front of the x squared cuts all those y's in half, producing new y values, not in red here, but in blue, of 0, because 0 times 3 is 0. 0 times 0.5 is 0. The 0 never changes when you're dilating or reflecting. But however, 1, 1 will become 1, 1/2. 2, 4 will be 2, 2. Don't believe me? It's right here. What's happening is this distance from the x-axis to that point has been cut in half because of the 0.5. No longer up 2, it's up, it's no longer up 4, it's up half of that. And the final point that we see, 3 comma 9, should be right here. So 3 comma 4.5, because 4.5 is half of 9. Now we're looking at horizontal compression. So if you want to write it down word for word, horizontal compression for A, where A is greater than 1, 2, 3, 8, 90, f of AX compresses the graph horizontally by a factor of A. So what you're supposed to notice here is that the A is inside the parentheses instead of outside the parentheses like it used to be. The 2x, the 2 is inside the parentheses, all being squared instead of being out here in front. If I were to write letter A with parentheses, it would have looked like that. 3 times the quantity, x squared. That's different than the 3 being inside the parent function. Right? So this is the second graph that you're going to look at back on Desmos. You're going to put parentheses 2x and square it. So notice the blue graph here has been squeezed inward, like someone put their hand on one side of that parabola, hand on the other, and then squeezed together and made it skinnier. And if you're thinking, well, it also got taller, I agree. We'll talk about that in a moment. Let's just see what this squeezing factor was. What happens to the points? 0, 0, nothing. 1, 1 moved. 2 comma 4 is no longer in its normal location. The blue is squeezed in, right? And 3 comma 9, just off the screen there, has also been squeezed in a little bit. How so? Well, I'm going to use some lines here over on the right that are going to look like, I'm just going to go across and up. Over 1, up 1. Now it looks like over 1/2, up 1. Right? Next point. Over 2, up 4. Now it looks like it only goes over 1, up 4. Remember that. 1, 4. Next one, 3, 9. Red. 3 squared is 9. But now it looks like I only go over 1.5 before I go up 9. So all of those backwards L's that you see there in red and blue have been squeezed and made skinnier. Now the input is 0 to make 0, 0.5 to make 1, 1 to make 4, and 1.5 to produce 9. Here's why. The function over here already has a 2 in front of the x. So before, I had to put in 1 to produce 1 on the red graph. Now I only have to put in 0.5 because the 0.5 goes in and says, well, I'm going to get doubled by the 2, and then I'm going to be squared. So I put in 1. Instead of putting 2 in to get 4, you only have to put 1 in because the 1 gets doubled before it gets squared. And now instead of 3, you only have to put in 1.5 because it gets doubled before it gets squared. So the inputs were all cut in half because of the whole number 2. That's the idea behind it. Horizontal compression. Okay. Looking at the fourth option here, which is, what if you have a decimal in front of the x before you square? Or what if you take the x divided by a number before you square it? Or what if you multiply x by a fraction before you square it? This is the one we already have graphed on Desmos. So let's see what it does. It's wider. The original parabola was x squared, and that's in red, and the blue parabola is twice as wide. Here's what I mean by that. Let's use our old key points again. 0, 0, 1, 1, 2, 4, 9. The x's are stretched out. 0, 0 didn't move. It never does. But 1, 1 is now 2, 1. 2 squared is 4, but because of this x divided by 2, or 1/2 x, or 0.5 x squared, they're all the same. Now, in blue, instead of going over to 2 to get up to 4, I have to go over to 4 to get up to 4. The x's are stretched out. Instead of going over 3 and up 9, the x has to go over to 6 to get up to 9. All right? 4 and 2, 1. It's like the parabola saying, well, I need to double my x's to get up to the same y value because this function has a 0.5 in it that I have to multiply by before I get squared. Right? So the function has something that's going to cut that input in half before you square it. So in turn, your x's need to be twice as large. If you find what I say to be repetitive, sometimes I just want to say it a few different ways to catch a few different learners. Like maybe if I say it one way, you don't get it. If I say it another way, maybe you do. So that's why I do tend to repeat myself a little bit. I'm trying to say things different ways to catch different people. Yeah, I just said it again, so I do repeat myself. Sorry about that. I'm going to stop the video, and we're going to do a few things.